Hello, people. Okay, so we're doing 5.6. We are doing power. Okay, now I've separated power into two lessons. Okay, so this will be the first lesson. The reason I've separated into two lessons is because there's basically two formulas for power. Okay, let me bring those up real. Okay, so let's look at the formulas for power. Remember, you're going to need to be good with this formula chart because you got to be able to use it on the test. Okay, there's no, I mean, you can memorize all these formulas if you practice, but being able to identify them quickly on the formula chart is probably the more pragmatic approach. Okay, so let's find power. Power is represented by P, yeah? And then on here, you would just find the P. That's a lowercase, so that's not the one we're talking about. Here it is, this one and this one. Today we're going to talk about this formula. And then for the second unit, we're going to talk about that for the second lesson on power. Okay, so let's just talk about what that means here. So what we have power is equal to the derivative of energy with respect to time. Okay, now let's just first remind ourselves what this means. The derivative of energy with respect to time. So if I give you an energy time graph, and it has some sort of graph here. The derivative of energy with respect to time will tell you power. So that would be what on this graph? That would be the slope, right? Because a derivative means slope. So if you take the slope of an energy time graph, that will give you power. Yeah, so if you just get that slope right there. Now let's see what that would give you in terms of units here. That would be joules. Energy is in joules, so it'd be rise divided by run, right? And time is in seconds. Okay, so our power in terms of units is going to be joules per second, which we call watts, okay? And I'm just going to put a capital W. That's how they represent watts, capital W, okay? So if they give you a graph of energy and time, the slope will give you power. Now, let's talk about that in a couple different ways, okay? Now, you know that the derivative of energy with respect to time is power. So then if you, kind of reverse engineer this, energy is equal to, okay, to get rid of the derivative, you need to integrate it, right? So energy so if you integrate both sides here, that cancels out my derivatives here, right? Just leaving me with energy is equal to the integral of power with respect to time. Yeah. So this is just understood when they give you this. Yeah. So on the formula chart, they give you power is equal to the derivative of energy. So you should just understand that the integral of power with respect to time is equal to energy. Yeah, so power is equal to the derivative of energy. Energy is equal to the integral of power. Yeah, and let's just remind ourselves what that would be. So if they give you a graph, so on this graph, you needed to have an energy and time graph, right, in order to figure out power. On this one, let's say you're given a power time graph. Yeah, and let's say that graph looks something similar, okay? And you want to calculate energy. Well, what does integral mean on a graph? Integral would be the area, right? So if they calculate that part, it would be base times height divided by 2 because it's a triangle. So if they give you a power time graph, the area of it calculates energy. Yeah? We've spoken about that in a lot of different contexts. Remember this one, this is the one that we just recently did. We said force was equal to the negative derivative of potential energy, right? With respect to distance. So on the flip side of that, we said that potential energy is equal to the negative integral of force dx, right? And that is just understood. When they give you a derivative, then you know the opposite of it is also a part of the formula charts that they give you, right? So these are the two right now that we will be doing. We have new, okay? Power is equal to the derivative of energy, or energy is equal to the integral of power. Okay, so write those two down. Now, there's three formulas that kind of come out of this, okay? So in case you need to use them. Okay, so we know power is equal to the derivative of energy with respect to time. Okay, now I'm going to write this in a more traditional physics sense, how you might see it in like a regular physics class before you enter calculus-based physics. Power is defined as this in regular physics, work divided by time. Okay, and you're wondering, okay, well, how is this the same here? So the derivative energy, if you think about that as an average instead of a derivative, you have the change in energy divided by the change in time. Yeah, that's basically the algebra way of looking at a derivative. Change in energy divided by change in time. Well, we know, if you remember, work is equal to change in energy, right? Change in energy. So we have the change in energy is equal to work divided by time. Yeah, that's how they're working with this. So now there's something else that comes out of this. So if algebra is here, if we're going to mess around with this algebraically, power is equal to the change in energy over change in time. Well, remember there's two types of energies you can use. You could use potential, you could use kinetic. So that leads me to two more formulas that kind of are just understood by this formula here. It could be the change in energy. I could be talking about kinetic energy divided by time. And this is change in time. I'm just putting time. Or I could be talking about change in potential energy divided by time. Now let's just see what these would be like. This would be mgh final minus mgh initial divided by time, right? So this is another formula to calculate power. I could be doing the change in potential energy divided by time, could calculate my amount of power. Or I could be doing the change in kinetic energy, which would be mvf squared divided by 2 minus mv naught squared divided by 2, all divided by time. Yeah? Or we said change in energy is the same as work. So it could be work divided by time. Okay, so from this one formula, they gave us this one formula on the formula chart, right? That one thing that's saying power is equal to the derivative of energy with respect to time. And from that one formula, we can conclude that power can also be created or calculated by doing the change in potential energy divided by time, or the change in kinetic energy divided by time, or work divided by time. And then also that one that we said earlier, which you can conclude that if power is equal to the derivative of energy, then energy is equal to the integral of power, right? So from this one formula comes four more things that should just be understood for the AP exam. These are not listed on the formula chart. These are things that you need to just have understood. So whenever they do derivatives like that, you just need to recognize this. Okay, so I could do opposite. It could be the integral, or it can kind of change up the derivative to an algebraic way of looking at it, and it'll come out looking at like different formulas, okay? So let's do a couple examples. Let's look at a couple. Let's talk about a light bulb. A standard incandescent light bulb for a house is 60 watts, right? Which means that, let's just understand what this means. A light bulb uses 60 joules of energy every second, right? Now let's say I want to convert that into what is 60 joules of work? You know, and then I can just think about I got to do that every second. So what is 60 joules of work? Well, let's think about that. I can think about it in a few different ways. Joules is energy, right? I can either think about it as potential or I can think about it as kinetic. Yeah? I'll mess around with it as potential. Okay, so we know, let's say we just want to see what 60 joules of work looks like. So we're going to use this formula. Now notice I'm just putting mgh divided by t, because what I'm going to do here is mgh final minus mgh initial. I'm going to say my final height, I'm going to say my final height is 0, because remember it always hits the ground, right? So I'm going to say like that's gone. I'm not even going to focus on that. I'm just going to focus on the part of where I'm lifting it to, okay? So let's just talk about like lifting something here, okay? So mass, let's say you pick up 1 kilogram. Yeah, let me get a kilogram. Okay, just to exhibit what 60 watts would be, let's say you have this. This is 1 kilogram. Okay, so I'm gonna lift something that's 1 kilogram. Gravity is 9.8, and we're gonna see how high I would need to lift it in 1 second. Yeah, in order for it to be 60 watts. Okay, so my formula is 60 equals 1 times 9.8 times h divided by 1. Okay, so the ones cancel. I divide by 9.8, so I get 60 divided by 9.8. That's about 60 divided by 10, right? So we're looking at about 6 meters, approximately 6 meters. So for 60 watts, for a light bulb to work, I would need to lift this thing 6 meters. That's about double my height, yeah, every second. That's what a light bulb is doing. It's using about that much energy every second. I know you guys have seen those bikes that when you ride them, it turns on a light. Well, there's other types of things that'll turn on a light too. You can actually hang a mass from something, and as that mass falls down, it turns something kind of like someone riding a bike, and it'll light up a light bulb, right? So if I held this from 6 meters, which is about 18 feet. Yeah, I'm sorry, about 6 meters, 6 times 3. 18 feet. If I hang this from about 18 feet up and I let go of it and it falls all the way down, gravity did work to light up a light bulb for 1 second. Yeah? Okay. Well, and that type of a light bulb. LED lights don't require as many watts or anything, okay? But that's the idea there. So you can calculate power based off of that formula right there, yeah? Potential energy. I just showed you how you could do it. Now you could also calculate it based off of velocities. So if it gives you a velocity, then you know you're going to be using this to calculate power. If they give you work or joules, you know you can use this. Yeah? So let's just look at the worksheet real quick, and we can just kind of look through some of them and determine what formula out of the multiple formulas that we have right now, 5 of them, the one formula that was given to us, the one we could conclude based off of that formula, and then the algebra ways of looking at each one of these, the algebraic ways of looking at each one of these. Let's kind of look at the worksheet that I'm giving you guys, and we can kind of identify which of those 5 formulas you would be using based off of the information given, right? So a 1,000 watt motor lifts a 100 kilogram object. Okay, so it gave me 1,000 watts. That's power, right? Lifts a 100 kilogram, that's a mass, object at a constant speed. How far up can the motor move the object in 10 seconds? It gives me a time, right? It wants me to figure out how far up it can move. Now, some of you might be looking at this constant speed thing. Yeah, but the only reason the constant speed is given there, it never tells us what the speed is, right? We could calculate it if we wanted to in certain situations, but if it says a constant speed, then I know that the force going up is equal to the force going down. So there is there's a cancellation there. Okay, so what I want to know how far up it can be moved. So I want h, I have time, I have m, and I have power. Okay, so based off of that, I would hope that you're looking at this and going, oh, that looks like this formula. So I'm going to set this formula up, kind of like how we did here. Yeah? Okay, looking at the next one. A motor produces 1.4 watts of power. So I got a power. How much time will it take for the motor to lift that mass at a constant speed, so same thing as it was doing in the previous one, a total of 2 meters. So it looks like I'm going to be using the same type of formula, yeah? Except on this one, it looks like I'm trying to solve for time. So I'm going to be using that same formula here because I'm given mass, I'm given height, I know gravity, I know power, I can solve for time. Okay, let's go to number 3. An engine is moving an object with a power given by this formula. Okay, now guys, whenever they give you a formula, so we did these based off of points, Yeah, that's when you're doing that based off of points, you're doing algebra. When they give you a formula, then you can start doing calculus because now you can do derivatives and integrals, right? So if they give me a formula, I'm either going to be plugging into the formula to get my answer, or I'm going to be doing a derivative or an integral, most likely. Okay, so let's see what we got here. An engine is moving an object with a power given by this. Calculate how much energy the engine produced in the first 5 seconds. I want energy, right? So if I want energy, well, this isn't going to help me because I want to calculate E. So I need to solve for E, which means I need to do the integral of power with respect to time. So the integral of this in the first 5 seconds, so the integral from 0 to 5 would calculate how much energy is used. Okay, so to the right of is an energy time graph. Okay, we got an energy time graph. What's the average power during the first second? Okay, so I know that if I want power on an energy time graph, remember we spoke about that, that's slope. So I'm going to be calculating my slope for the first second. Okay, what is the average power delivered in the first 3 seconds? Same idea, right? Calculate how far the object was lifted off the ground in 3 seconds. I was going to change this. I'll leave it on there for now. Okay. A person is pulling an object across the floor with a formula. Okay, they give you a formula for energy. So like that thing again, I'm starting to think, okay, they gave me a formula. I'm probably going to be doing an integral or a derivative, where T is represented in seconds. Calculate the power derived from the person at that point. Okay. Now remember, derivatives are at a point. Integrals are for an interval. Because if you do an integral, like if you do an integral for an area here, you have to be doing it for some interval, right? Like 0 to 1. I need to have an interval to do an integral. Now the slope, you can find the slope at a single point, right? So I kind of was already thinking when I see this question, I see at, the word at, like I'm thinking, okay, well, I'm probably going to be doing a derivative or something, or plugging in the 1.2. But let's see here, calculate the power. Okay, well, if I want to calculate power, and I have the energy formula, the derivative of that energy formula gives me power, right? So that's what I'm going to be doing. Okay, next one here. A mule is dragging a box across a flat desert. The force the mule exerts by a distance is given by the the graph on the right. Calculate how much work the mule produces in 12 seconds. Okay, so how much work is produced on this force distance graph? Okay, well, on everything we just did, we didn't do force and distance anywhere, right? So what you're going to need to do is you're going to need to like revamp your mind, go back in time here. This is a question from before. And if you remember, I can't move the computer. I'm stuck to stuff. But let's look at the formula for work. If you remember, work is equal to, this is how the, and here, let's look at the, work is equal to, and let's just look at work done on a system is capital W, right? We need to find our work formula right here. Okay, work is equal to the change in energy or the integral of force dr, which r represents distance. Okay, so let's look at that. Work is equal to the integral of force with respect to distance. Okay, so how would we get the integral of force with respect to distance on a graph, like this? It's going to be area, right? So work is equal to this and that. So it'd be the area of that graph. Okay, on this one, they have a power time graph. It says calculate how much energy. Okay, so that's that same idea. We want to calculate energy. You want to calculate energy, and you have a power time graph. So the integral of that would calculate that. I kind of created this question to kind of set you up to then do an area on that one. So you're doing area on both of those, right? And then this one to the right is above when the mass is released. Calculate the spring constant. Okay, so you're going to be using on this one. So this object falls and hits this thing and this spring and compresses it a bit. I want you to calculate what the spring constant is based off of it compressing 0.1 meters. So what you're going to want to use here is use energy, okay? Conservation of energy. So if you're thinking of like, well, what the heck are you talking about conservation of energy? That's going to be that mgh plus mv squared over 2 equals mgh plus mv squared over 2. And you got two different situations, right? You got point A and point B. Okay, so here, where it's being released will be our point A. And then once it's compressed it all the way, would be your point B, right? So when it's being held up, the block is being held up, there's no velocity. So all it is mgh, okay? And the m will be the mass of the object, which, what is it? 1.5. Gravity, 9.8. And the height is going to be 0.6. I know some of you are probably looking at it and saying, no, it's 0.5. But it's actually, it's from where it stops. So it's 0.5 plus 0.1. So that's 0.6. And then equals, you know, your mass times gravity times height. Once it's compressed, there is no height. Yeah, you're going to call that height. You're going to call that 0. You're going to say, like, that's the ground. Okay, and then actually, sorry, I don't even know why I said it equal to this. Because there's no velocity either, right? Once it compresses all the way, it's stopped. But you're trying to figure out what the spring potential is. So there's actually another, right? There's like another thing here. That's where we're going to set it equal to the spring potential energy, and we'll plug in 0.1 for the compression that it actually caused. And then you can just solve for K, right? There is no spring potential energy on this side because there's no spring, yeah, so it's at the start, so I don't need to worry about that because there's no compression of a spring or anything. So there's how you would do that one. I hope it all made sense, and talk to you later.